section 6.3, we're going to talk about the eigenvalues and the eigenvectors of symmetric matrices. And here we have an amazingly strong theorem which will state right up front. And I should say that I'm not going to follow the book particularly closely for section 6.3 because we're nearing the end of the course, and I just want to summarize, just want to highlight a few interesting facts about symmetric matrices. And this theorem is really the punchline. So it turns out that if you are given a matrix that's square, so it has to be square, of course, because we're talking about eigenvalues and eigenvectors, then it turns out that if the matrix is symmetric, which of course is this property here, so this means simply that A is symmetric, then there exists an orthonormal basis of eigenvectors. So another way of writing this is that A is diagonalizable. So you can write A as a product of an orthogonal matrix, a diagonal matrix, and then the transpose of the same orthogonal matrix that you started with. Another way of expressing this is where I started, saying that there's an orthonormal basis of eigenvectors. So these are the UJs, and each one of the basis vectors is an eigenvector, like this. And notice that this is far stronger than the statements we could make about a general matrix, where in general you don't even know that there exists any real eigenvalues of a matrix. But if it is symmetric, that not only do the eigenvalues exist, but you can actually express, you can build a basis, an orthonormal basis, so that any vector can be written as a product of eigenvectors. And this is super helpful because the action on an eigenvector is just scaling. So it's very easy to understand such a matrix. So if we want to look at the matrix at this theorem a little bit more closely, then notice first of all, so note that 2 and 3 are just reformulations of the same thing. They're really the same statement, because if you take your basis and you put them as columns in a matrix U, and then you form a diagonal matrix by putting the eigenvalues on the diagonal, then AU is AU1 up to AUN. And now if the UJs are eigenvectors, then these are just scalings. So AU1 is lambda 1 U1, AU2 is lambda 2 U2, and so on all the way up to, so these are all columns, like this. And that is, of course, U right multiplied by the diagonal matrix with eigenvalues. So that's U times D. So from this equation, this is the same whenever U is invertible as A is equal to UD, U inverse, and since U is orthonormal, the inverse is just the transpose. So point here being that 2 and 3 are perfectly logically equivalent. There's nothing to prove in saying that 2 implies 3 or 3 implies 2. They're just different ways of writing the same thing, once we've established the properties of orthogonal matrices. And the other thing to note is that the fact that 2 implies 3 is also trivial. That if A is UD, U transpose, then A transpose is U transpose transpose D transpose U transpose, and since U is orthogonal, for any matrix, the double transpose is just U. Since D is diagonal, D transpose is D, U transpose is itself, and that's A. So the fact that 2 implies 1 is perfectly trivial. So the interesting fact is that this is the part that needs to be proven. That if the matrix is symmetric, then it is, you can go either to prove 2 or to prove 3, but in either case, the point is that you need to prove that there is a full orthonormal basis consisting of eigenvectors. We're not going to do the full proof, but towards the end of today's lecture, we'll talk a little bit about what properties make this possible. But before we leave this slide, let's mention what does this mean in terms of the representation of a matrix. So if you use the basis, so this is another note, a consequence, if you will, of this theorem, that if we set B to be these vectors uj, so this is the basis. And then we consider the map, so consider the function L that goes from Rn to Rn. This is the linear map. L of x is just a times x. Then if you use the basis B, so in the basis B, the matrix associated with L is D. So it's a diagonal matrix. That should not be a curly D. It's just plain D. So this is very interesting. That so remember that you have on the one hand the concept of a linear map. So you could take, so this is, think of this as an object that takes a geometric vector, say, and maps it to another geometric vector. Then once you fix the basis, then this linear map corresponds to a matrix. And if you use the standard basis, the canonical basis, then the matrix representation is A. But that's not the only basis that exists for Rn. In particular, if you choose as the basis the eigenvectors, then you get the very useful fact that the linear map L becomes a diagonal. It's a coefficient matrix is a diagonal matrix, which means simply that it's a rescaling of the diagonal. So notice that if you apply D to some vector y, then the effect here is simply to scale each one of the variables by the corresponding eigenvalue. So this is pretty much the simplest form of linear map you can think of, from Rn to Rn. All right, let's do perhaps an example before we proceed. So let's look at this matrix. So A is the matrix 1, 3, 3, 1. And you can easily compute the eigenvalues and the eigenvectors. So there's one eigenvalue that's 4, and this corresponds just to the eigenvector 1, 1. And the other eigenvalue is -2, and that corresponds to the eigenvector 1, -1. Actually, we needed to scale them, orthonormal I said, so notice that the way I wrote it, u1 has length √2. So I need to divide by √2. Let's rewrite. Okay, that's better. Now I've scaled the eigenvectors so they have length 1, and then the matrix U becomes 1, 1, 1, -1, and D in this case, so this is the matrix that has the eigenvalues on the diagonal, so this is 4 and -2. So now, so if you use, so in R2, you have your standard basis. So if you use E1 and E2 as your basis, then the matrix representation here is what we started with. But now the point is that if we instead, so the statement here is that a particularly nice orthonormal basis is to work with U1 and with U2. Or actually I did U2 a little differently. My U2 goes like that, doesn't it? Because in this representation, so if you use these bases, then the linear map has D as its coefficient matrix. Okay, so this is very nice. So basically when you're working with a symmetric matrix, it's sometimes very convenient to use its eigenvectors as your basis. So let's talk a little bit about why it's useful to have a diagonal representation of a matrix. So say A is UD U transpose for U orthogonal and D diagonal. And this will be really just a review because we already talked about this. So one important consequence is that if you take powers of A, then observe that the U factors cancel. So this is UD U transpose is UD square U transpose. So remember, so this works more generally. So you don't need the basis to be orthonormal for this. It's enough to have simply this. But what makes things particularly handy is that for symmetric matrices, you know that this representation, it must exist when A is symmetric, whereas this representation need not exist in general. There are special cases. If all the n eigenvalues are distinct, for instance, then you know that there exists such a representation. But it's much more convenient for symmetric matrices, because then you know that such a representation exists necessarily. And of course, you can continue this. And in general, A to the pth power is U times D to the pth power times U transpose. And of course, D to the pth power is just the diagonal entries to the pth power. So these are very easy to compute. And you can push this even further. So say f is an analytic function. So f of t is equal to some not sum over t, of course, p perhaps. So if you have sum like this that's convergent, absolutely convergent in some interval around the origin, then I can now define f as acting on the matrix by just plugging it in the same power representations, the C of P, A to the P, and now I plug in the diagonalization and you get like this. And since each term involves U multiplied from the left and U transpose from the right, I might as well pull them out. Like this. And now you see, since these are diagonal, that this is just f acting on the diagonal values, on the eigenvalues. Okay, that transpose should not be there. So U makes up. All right, so you can in general define a function of a symmetric matrix. And in particular, you can define, say, f is the exponential this is 1 over p factorial t to the p, then f of a. So you can define the exponential of a matrix through the powers. The series converges absolutely as well. And then this works out to be simply u acting on the left. And then you have the exponentials of the eigenvalues on the diagonal. And then u transpose. Okay. So if you're given a symmetric matrix, you know you can compute the eigenvalues and the eigenvectors. And then you can do all sorts of interesting things. So for instance, you can compute the exponential of a matrix. Why do we care about that? So one application of this is to solve systems of ODEs. And I know a couple of you have seen this already in prior coursework. So let's just connect it. So first, recall that if you have a very simple, so the simplest possible differential equation, if x is a function of t, and you have the equation dx dt is equal to simply a times x of t, and then you have some initial condition, x of 0, some initial value, x0, then the solution is e to the at, like this. And now we can generalize this to systems. Now, say you have a whole vector of functions, like this. So this is a set of n functions. And now we consider say we have x dot, yeah, let's use that notion of a derivative. So we have this equation. So notice now this is a vector n times 1. This is a matrix n times n. This is a vector n times 1. So I hope nobody's confused. X dot of t is just d dt of x of t. Then the solution is x of t is x at the point 0, or first we write the exponential of t times a acting on the vector of initial values. So of course I'm going very fast here, and this is really just to give you some idea of how these things can be used in applications. I mean, we're not going to go through system of ODEs in any detail. I'm just going to mention it on this slide, and we're not going to discuss it further. This is the last lecture, so I just want to make some connections to things you may have seen before, and if not, we'll very likely see in later coursework. So let's maybe make an example here. So say we have x dot 1. Let's use the matrix we had before. x2 dot is 3x2 plus x1. So in other words, x1 dot, x2 dot is equal to 1, 3, 3, 1 times x1, x2. Now this is your matrix A. And now we can write down the solution as x of t is the exponential of t times a acting on the initial values, and this is u exponential of td, u transpose acting on the vector of initial values. And using the formula, let's see, do I have space? Maybe. Let's see, this may or may not work out. So now I'm using, so remember the eigenvalues in this case were, what were they? -1 and 3, right? Let's go back and look. No, they are 4 and -2. I'm glad I checked. So I remembered correctly the first time. So lambda 1 is 4. Lambda 2 is -2. Yeah, it's obvious, right? If you multiply a by the vector 1, 1, you get 4, 4. And yes, this should be right. And then we get e to the -2t. And then u transpose is u in this case. And the whole thing multiplied by the vector of initial data. Okay, so this whole shebang here is the exponential of t times a. And again, I'm really just mentioning this so that you have some awareness of the existence, that you can define things like the exponential of a matrix. We're not going to talk about this further. So before we close this little discussion on eigenvalues and eigenvectors of symmetric matrices, let's talk a little bit about what are the properties that make all this possible. So let's start with establishing a little lemma about how symmetric matrices interact with the dot product. So maybe formulate it as a lemma. So say A is a symmetric matrix. So A is a transpose. Then if x and y are vectors in Rn, then the inner product of Ax with y is the same as the inner product of x with Ay. Proof here is super simple, that if we think of x and y as column vectors, then we can write this as Ax transpose times y. And now we use the properties of the transpose. So this is x transpose, A transpose times y. And here we use that A transpose is equal to A. So this is x transpose times Ay, which by definition is just the inner product between x and Ay. Okay, so here's it's a very simple fact about symmetric matrices. And this is actually how you define a symmetric operator in a general what's called inner product space. So this works not just in Rn, you can do this in much greater generality. But let's keep things simple and stick to just Rn. Then the second theorem we're going to mention is the following. So let A be a symmetric matrix again. So notice when I say A is equal to A transpose, that in particular implies that it's square. And now suppose lambda 1 and lambda 2 are two eigenvalues. So A u1 is equal to lambda 1 u1, and A u2 is lambda 2 u2. Then if these two eigenvalues are different, then the corresponding eigenvectors are orthogonal. In principle, I guess I should have made the assumption that u1 and u2 are not 0, because in that case they wouldn't be eigenvectors, but if they are, then the inner product is going to be 0 anyway. So I don't think we need to exclude that case. But of course, that one is not very interesting. So the proof here is really super simple. So lambda 1 times u. Okay, So what am I doing here? I want to prove that this is 0. And just as a little aid in the proof, I'm going to pre-multiply it by lambda 1. And now we're going to do a calculation, and that's going to lead to an equation that implies what we want. So, right. So the fact that I start with u1.u2 is very natural. That's what I want to prove something about. My pre-multiplication of lambda 1 seems maybe a little random at this point, but you'll see that it's going to work out very well. So now this is equal to, I can of course write that as lambda 1 u1 in a product with u2. And this is a u1 in a product with u2. And now I use the little lemma, so this is u1 in a product with a u2, which is u1 in a product with lambda 2 u2. And I get this equation. So now this I can write as lambda 1 minus lambda 2 times the inner product between u1 and u2 is 0. And by assumption, I know that that's not 0, so then it follows that it must be the case that u1 dot u2 is 0, which is precisely what we wanted to prove. So, what does this mean in words? If you have two eigenvectors associated with different eigenvalues for a symmetric matrix, then the two eigenvectors are orthogonal to each other. Here is another interesting statement. So again, let A be a symmetric matrix. Let lambda be an eigenvalue of A. And now we set M to be the eigenspace associated with lambda, so the set of all vectors such that Ax is equal to lambda x. And we let N be the orthogonal complement to M. Then what's interesting is that if x is a vector in M, then Ax belongs to M as well. And if x is a vector in N, then Ax remains a vector in N. So the technical term here is that M and N are invariant subspaces of the operator A. That if you act with A on vectors in M, then you don't go outside of M. And the same thing in N. Now the proof here is, for part A, it's completely obvious. If x belongs to M, then Ax is just lambda x, right? So of course this is in M. Very simple. Because M is a linear subspace. So of course, if x is in M, then lambda times x is in M as well. For the other one, I've run out of space, so let me delete. So pick x in N, and then fix any y in M. And what I need to prove is that Ax is orthogonal to y. And since if this holds for every y, then that means that Ax belongs to the orthogonal complement of M. So we need to prove Ax in a product with y is 0. Well, Ax dot y is x dot ay. No, sorry, the other way around. No, it is, no, so this is good. So Ax in a product with y, I move A over to hit y. And now since y belongs to M, I know that AY is equal to lambda y. So this is lambda times x dot y, but since x belongs to n, x belongs to n, and y belongs to m, and these are orthogonal complements. By definition, this turns out to be just lambda times 0. So this is all 0. So what this means is that if you find one eigenvalue, one eigenvector of A, then the line, the one-dimensional subspace that's spanned by that eigenvector is an invariant subspace of A. And its orthogonal complement is another subspace. So this means is that you can peel off the eigenvectors one after another, and they each act. A is just a scaling in each subspace that you pick off. So this is the general idea. And in order to make everything work, you need one more little technical detail. Let me erase to create space. All right, let's just write the name, because this one doesn't depend so much on the others. So there's one, if you want to prove the spectral theorem, you need one more preliminary result. So let A be a symmetric matrix and set mu to be the supremum over the set. Okay, so let x be a vector, and then I form the inner product between x and ax. I take absolute values, and I do this for all x that have length 1. All right, so this is just a set of real numbers, so, and it's bounded, and therefore it must have a supremum. So this supremum mu, it certainly exists. It exists for any matrix. But what's interesting is that when A is symmetric, is the following. There exists a vector u that has length 1, and this vector u is an eigenvector of A, and lambda here is either mu or minus mu. So for any symmetric matrix, you can always find one eigenvalue for it. And this is proven in the book. And then the idea is really just to combine this statement with the other ones on the previous slide. And then there is an induction proof by which you can prove the spectral theorem that we started with. And these things are very interesting. We are right at the end of the course. I'm not going to go through this in detail because that would really, we're out of time basically. I wish we had time to talk more about these things. They're super interesting. I encourage you to read section 6.3 in the book. But I think if you read this lecture, then you got the basic ideas. So the main takeaway. So if the last couple slides were a little confusing, if you're stressed, don't worry about it so much. This is really more to connect things to future coursework for you. But the one thing I want everybody to take away from this lecture is this theorem, because this is super important. This you're going to use a lot, hopefully, going forwards. This theorem pops up all the time, because in physics, for instance, many operators acting on infinite dimensional spaces turn out to be symmetric or self-adjoint, as it's called in a more general space. And there's the variations of this spectral theorem that apply to such operators. So basically a lot of quantum physics, of the classical quantum physics, is based around classical spectral theory, and the two of them were developed pretty much hand in hand. So the different states, if you write down the Schrödinger equation for a molecule, then its different states corresponds to different eigenvalues, and there's really an extraordinarily close connection. Again, things like this, it comes up in data analysis. If you've seen things like the original PageRank algorithm, they form a gigantic matrix, and you can modify it a little bit to create a symmetric matrix. Therefore, you know that it has eigenvectors and eigenvalues, and the eigenvectors associated with the largest eigenvalues turn out to be very helpful in finding websites that had a lot of what they call authority. So what they helped you define what were good hits to different words. And really, spectral theory comes up all the time. In structural engineering, it's, these are, if you have a big structure that might buckle under a heavy load, then the load at which it buckles is the lowest eigenvalue of the energy matrix for the structure. And there's just a gazillion different applications of this. So I know that this lecture went very fast, and it was really just intended to give you a flavor of the kind of things that come up. But this theorem is really super important. So please make sure that this is something you'll remember after you complete this course. All right.